compartment. Didn't talk about a shoulder compartment. There is a shoulder compartment, but I'll let you get away with not learning that. But pelvic compartment is pretty easy because you've got the pelvis taking up the mass on the middle side of that circle. So you're going to have something that implies acetabulum here, and that will have connective tissue coming out laterally, and you'll end up forming an extensor compartment posteriorly and a flexor compartment anteriorly. So what you have posteriorly, gluteus maximus, you have the hamstring muscles, those are your hip extensors, and then in the anterior compartment, iliopsoas and rectus femoris are your primary flexors. So here they have the section taken down in mid-thigh, so it's not the pelvis. So mid-thigh, you're running into the femur, so one bone in the center. But instead of the connective tissue going straight across as you had in the humerus, now you have a middle compartment that contains the adductors of the hip. You also see that the flexors have now moved to the back of the femur, and the extensors are now on the front of the femur. And that's because when you're born, your little baby legs are actually pointing in that direction. And then as you rotate and extend down so you can walk, your extensors come to the front and your flexors go to the back. And that's functional for upright ambulation. So you have to get that medial rotation and then extension down, and that's what the toddlers are learning to do. So you watch them, their toes are still pointed out, they're not very efficient in walking, and as they get this rotation occurring and the toes point more anteriorly, then they take off and really can run. So when you see one bone, 3 compartments, with a medial compartment, that will be your adductors of the hip. So adductor magnus, longus, and brevis. Flexors of the knee, these are 2 joint muscles like the hamstrings, and then biceps femoris, the short head. And there will also be some that will be from the lower leg that are crossing the knee and help with knee flexion as well. Knee extensors, this is going to be your quadricep muscles. Those are your major knee extensors. So now you can see vastus intermedius, you see vastus lateralis, vastus medialis coming around from the back, and then rectus femoris on the front of the thigh. So knee extensors front, knee flexors in the back, medial compartment, knee hip adductors. The lower leg, you then have 2 bones. Tibia is always bigger than fibula, so small bone, large bone, connected by interosseous membrane. The compartment, there's 3 compartments here, but there's a lateral compartment. And that's your everters of your foot, those are your fibularis muscles. And then posteriorly we have flexors now of the ankle, and some of them come from above the knee so they can also flex the knee as well. And then dorsiflexors of the ankle, those are, the main dorsiflexor is your tibialis anterior, but anything that dorsiflexes the toes is also, since it's crossing the ankle, that also will participate in dorsiflexion of the ankle. This compartment here is surrounded on 2 sides by bone, and then it's layered with multiple muscles posteriorly, and bone and muscles anteriorly and laterally. That compartment is the one that you have to pay attention to the most. So you get a line drive in golf to the back of the ankle. I've actually seen that and watched golf tournaments, and somebody in the audience, some guy shanks the ball and it goes right into the audience, and they see it coming, they turn and whack right in the back of the calf. So you got this big cherry red lump on the back of the calf. Line drives in baseball, that also right in the back of the calf. And that swelling, superficially, you may be able to control with ice, but the deep compartment, you're not going to reach with ice. You've got to reach it with medication. And so if the line drive is to the back of the calf, you don't hesitate. You send that person to the ER to get treatment. If you ice it and they say, oh yeah, I feel fine, I want to go back and play, if that ice didn't reach that swelling, 2 days later they've got foot drop and they've got weakness and they've lost the function of the deep muscles. It's too late now. So you've got to get it treated right away. And athletes, they're very motivated to get back into the game, but as a trainer, as a team doctor, you got to say, get it treated, go to the hospital and get it treated. So, and acute compartment syndrome, due to that kind of trauma, it's limb threatening. It can actually become life threatening. You can actually die from deep compartment syndrome. The limb is threatened because perfusion pressure drops due to the swelling impinging on the blood vessels, so you don't get blood to the tissue. And then if the tissue dies and becomes necrotic, little bits of that can get into your circulatory system, cause renal failure, and you either go on dialysis and wish you were dead, or your kidneys fail and you do die. So it's a severe condition. You want to get treated. Chronic exertional compartment syndrome occurs in athletes that are involved in repetitive loading that is causing repetitive exertion. So the extremities, any extremity can be compromised by repetitive loading and repetitive exertion, but most commonly it's occurring in the lower extremity and occurring in runners, like cross-country runners, endurance runners who don't get adequate rest. So muscles that are in this deep compartment, there's a lot of them. There's the upper calf, you have popliteus that locks and unlocks your knee. You got flexor hallucis longus that controls your big toe. Big toe is important for stability. Ask anybody who's lost a big toe how hard it is to learn to balance again without the big toe. Flexor digitorum longus, all the toes will then not be able to grip and balance will be compromised. Tibialis posterior is an inverter of the foot and also a plantar flexor. And then the artery actually goes across to the anterior compartment, and that can affect the anterior tibialis. And the nerve also goes posterior and anterior, so you can lose the nerve. So you can lose the blood supply, you can lose the nerve supply. So right in this compartment, that's where the tibial nerve splits to go anterior and continue down posterior. We've got to treat that. Okay, chapter 12, I've pared it down so that you just have to know what I'm showing you about the surface of the body, and you don't have to know anything else in chapter, am I still listening there? In chapter 12. So I've already posted what you have to know, so I'm just going to run through it really quickly, tell you why I think it's important you know about these structures, if you're going to be a judge for power for bodybuilders, you need to know your surface anatomy so you know what muscles are developed and what muscles aren't developed. But then also if you're going into any kind of being a trainer, a physical therapist, or a medical doctor, you need to examine superficial anatomy to know, and you have to know what's normal and then what is looking abnormal. So during a medical examination, you are going to be assessing the superficial anatomy. And this it can be invasive. You can go into orifices and things like that, but mostly you're doing it as a non-invasive assessment. You're estimating approximate anatomical locations of certain internal organs based on the superficial position of muscles externally. And then you're going to palpate in to feel deeper structures. So for example, females, guys, ask your girlfriend about the examination of their ovaries. The physician doesn't go in there to examine the ovaries. He finds the iliac crest, goes medially, and then palpates deep in there, and he can feel the ovaries. So you know your superficial anatomy, you can find these structures that are invisible to your naked eye. The head and the neck, up here in the temple, there are blood vessels that you can compress against the bone, and you can feel pulse there. You can feel pulses behind your ear. Anywhere you can compress an artery, you can feel a pulse. You press in this area right between your sternocleidomastoid and your scalenes. You can feel the carotid artery pulse there. Also in that area more superficially is the jugular vein. You're not supposed to see pulses in your jugular veins, but if you know you're not supposed to see a pulse there, you actually have to feel the pulse in your carotid artery by compressing the artery against the muscle or the bone. So that's the only time you feel a pulse. You see a pulse. That's a pulse in the jugular vein. That's a serious heart problem that you have, and that's something you want to get treatment for. You at least want to mention it to the individual. Have you ever noticed you have a pulse here? If they say no, they say, well, you do have a pulse there. If you haven't ever had it checked out, you need to go and get it checked out, because it means that the atria is pumping against a closed valve, or it's pumping against a ventricle that's not empty. If the ventricle doesn't empty, the blood doesn't come back to the left heart. If the blood doesn't come back to the left heart, it doesn't go systemically. If it doesn't go systemically, lack of oxygen here, pass out. It doesn't go out to the rest of your tissues are hypoxic, may start to fail. That's a serious condition. So know where your external jugular vein is. If you see a pulse in that area, then that person is in trouble. Brachial plexus, sometimes people have symptoms in their hands. And the problem is not in their hands. The problem is up here in their neck. Like those people who snap their necks from side to side, and people who walk around with their head forward. Sometimes they get numbness and tingling and weakness in their hand. It's because of compression in the nerve. You can manipulate, you can actually press in there, and that's the location of your brachial plexus. You can mess around in there and see if compression of the nerves right next to the neck aggravate the symptoms. If they do, then you know the problem is in the neck region. If you then go out to, it's not a problem here, you can do the same thing in the elbow area. Maybe it's a problem with impingement here. If it's not a problem there, check out the wrist. It might be a problem here. It's usually not a hand problem. It's usually a neck problem. So you need to know where to find your brachial plexus. The suprahyoid triangle, we've mentioned all the muscles that are connected to the hyoid bone from above. So know that triangle. The submandibular triangle, those will be important next semester. The superior carotid triangle, that's where you take your carotid pulse more likely, so know that. And then the inferior carotid triangle, you can take a pulse down there, but it's much harder to locate. So mostly know that the suprahyoid triangle and the superior carotid triangle. Also know how to locate the major blood vessels in the arm. Up in the axillary region, if you want to ever incapacitate somebody who's giving you problems, if you're a lifeguard and you have to do a cross chest carry and the guy starts fighting you, just reach in the axillary region and grab the nerve, and that will usually stun them and they'll quiet down so you can get them into shore. I mean, it's your life and their life, so if they're going and not struggling, then you can get them to safety. So it really is important to know that, but you also want to know that there are blood vessels there are nerves there. You want to examine them at certain times. Also in the forearm, there's some medtech people here. You're going to be doing phlebotomy. You need to know the location of the nerves, this antecubital fossa. You're going to have the median cubital vein. Maybe that's where it's nice and straight. You can stick in a needle to get blood. You're just going to find the vein superficially and then find the one that is the straightest and most easily accessed to then take blood from. Our database has been updated. Oh, that's nice. Yeah. So, woohoo, it's updated. Okay, and then out at your wrist, most of the time you're taking a radial pulse. You can take an ulnar pulse as well. And you just compress the arteries against the bones down below, and then not so hard that you cut off the pulse. I'm up here if you grab the nerve. But anyways, you're taking a pulse. You just want to compress the blood vessel so the pressure has to build up and then squirt the blood underneath your pressure, and that will give you the pulse sensation. So radial pulse, ulnar pulse. And you can also take pulses of the radial artery too. So that might be something that you want to examine. If you have a severe injury to the lower extremity that is bleeding profusely, you need to know this triangle up here. You need to know where to get that femoral artery and compress it. So if somebody's spurting blood from their foot or from some lower extremity injury, you gotta get the palm of your hand, you gotta lean into this triangle and cut off that femoral artery. Until paramedics can get there, you gotta put that pressure on and limit the blood that's gonna be leaking out. So the popliteal, also, if somebody has numbness and tingling or their lower extremity is pale, it doesn't look normal color, you want to find out where the blood supply is being compromised. It might be up at the femoral region, but it might be in the back of the knee as well. So you want to feel for a pulse behind the knee. You feel a pulse there, then blood is going by the knee. So then you want to examine down below. So you want to take posterior tibial artery, feel for a pulse there, or feel for anterior tibial artery pulse. So the foot is pale, more than likely, and the leg is not, more than likely it's a compromise in the ankle. But you don't really know, so you want to feel for a pulse in the popliteal area as well. So examine the pulses, and usually that's what the typical places for examination of somebody who may have heart problems, circulatory problems. You want to just be sure that there's adequate blood supply everywhere. So check for pulses everywhere. Okay, I haven't mentioned to this class, and I will show it to you now, and I will send out an email about the muscle origin and insertion. There are 18 muscles, 18 muscles on the list. You don't have to memorize all of them. I'll tell you the specific ones that you have to memorize. When I tell you to memorize number 16, then you memorize everything about it. You know it verbatim, forward, backward, upside down, and just know it word for word. I'm going to cut and paste into the test. If it's going to be true, I'm going to leave it alone. If it's going to be a false statement, I'm going to make it obviously false. So the insertion, instead of the iliotibial tract, maybe I'll say it's behind the knee or something. Well, that's not quite. So maybe I'll say it's on the ankle or something like that. So it's going to be pretty false. Yesterday I said deltoid attaches anteriorly to the humerus. If I said it was attached to the coracoid process, that would be false, because it's working the shoulder. It has nothing to do really with your coracoid process. The false statement will be obviously false if you know what these origins and insertions are. Sometimes there are two joint muscles, so you can have action from above and below. So so let's see. Just trying to find an example of that. So trapezius action from above, and then there will be an action from below. So you look for that, know those specific things. The rest of the muscles that we've talked about, I'm going to talk about the ones that are usually superficial, but if I went into detail about a middle layer or a deep layer, then you have to know those as well. You have to know the origins and insertions of the others that are not on this list that you're required to memorize. You have to know them well enough to know their actions and also where they're located on the body for identification purposes. But the specifics about the transverse process of C1 through C4, that you have to memorize from this list. Attaching in the neck region to something else, then that's good enough for the others. So there's very specific origins and insertions here. And I think Martini still has your gluteus medius and minimus incorrect. He has them both attaching to the same side of the greater trochanter, and they're both then going to be a medial rotator and They're not ever going to be an abductor because they're always going to be a rotator. So if you want to get gluteus medius and minimus to abduct, you have to have them attached on the opposite sides of the greater trochanter. Okay, I know you're going to ask me 100 million times before the exam about that, and you can email me and I will repeat. You only have to memorize the muscles on that list, the ones that I tell you to, so about 8 or 9 on that list. And then the rest you just have to know the origin and insertions well enough to be able to identify the muscle, and also if you didn't memorize the action, then figure out what the action is based on the attachment.
And you're going to send us that in an email, is that right?
I will send that in an email. Okay, now comes the hard part or the easy part. Depends on how, why is this not opening?
Is it present or present?
The dialog box is open. What is the dialog box? I don't know what the dialog box is. Is that the dialog box? There it is. Okay. So now the dialog box is closed. And just want to make sure I have the right file open. Yeah, okay. Okay, so we've gone over this already in Martini. Skeletal muscle, cardiac muscle, cross striations. Skeletal muscle, peripheral nuclei, multiple nuclei per cell. So cardiac, single nucleus, center of the cell. This lighter area around the nucleus of the cardiac muscle cell is where a lot of glycogen is stored. And this then takes up some space. The sarcomeres are pushed more laterally in that area. Intercalated discs, another identifying feature of cardiac muscle. That will be the location of desmosomes that keep them tightly attached to each other. Smooth muscle, smaller than cardiac, tapered at the ends, so fusiform. No cross striations because actin and myosin are going in multiple directions. So when smooth muscle contracts, it contracts from every single direction. Cardiac and skeletal contract in towards middle. So they're limited in one direction of shortening. Smooth muscle can contract towards the middle, from the ends, can contract from the middle of the cell, so transversely, and also obliquely. So much better function for things like sphincters, when you get contraction of the muscle from all directions. Not going to load.
And in moving the body and its assorted parts. The long cylindrical cells have many transverse stripes.
Start again. That's kind of loud.
Skeletal muscle tissue is the main tissue of muscles attached to bones. It functions in maintaining posture and in moving the body and its assorted parts. The long cylindrical cells have many transverse stripes, or striations. These represent many repeating units of the contractile proteins actin and myosin. Smooth muscle tissue is in the wall of the stomach, lungs, and other soft internal organs. Its contractions are slower than in skeletal muscle, but they can be sustained longer. They function in gut motility, urinary bladder emptying, sphincter closure, blood flow in arteries, and other internal organ activities. Cardiac muscle tissue is a contractile tissue present only in the heart. Its muscle cells contract as a unit, owing to signals at gap junctions where their plasma membranes fuse together. When one cell gets a signal to contract, others are stimulated to contract too. Now let's check what you have learned. Drag the text to each graphic to describe that muscle's function.
So where is it? Only heart. Cardiac, which is on. Okay. What moves bones? And stomach wall?
That's correct. Skeletal muscle is striated, and it interacts with bone. Smooth muscle consists of tapered cells, and it lines soft internal organs. Cardiac muscle cells are somewhat striated, connected by gap junctions, and occur only in the heart.
We've gone over sarcomere structures already. Here, they're pointing out to you what I told you, that each thick filament is surrounded by 6 actin. Each thin filament is surrounded by 3 myosin. The sarcomere goes from Z disc to Z disc. The actin is attached to the Z discs. The myosin is supported in the center by myomycin, which is that protein that holds the tails of the myosin together. And then the myosin heads are polarized in opposite directions from that center. I band will be the lighter areas where there is only actin. The A band will be where there's a zone of overlap plus the bare zone of the myosin in the center. When you bundle the sarcomeres together, you have you have a myofibril.
Skeletal muscle is composed of bundles of muscle fibers enclosed in a sheath of connective tissue. Each muscle fiber is composed of thread-like myofibrils. Each myofibril is functionally divided into many sarcomeres, arranged one after another along its length. Dark Z bands define the ends of a sarcomere. The sarcomeres are the basic units of contraction. A muscle cell shortens because the sarcomeres within it are shortening.
Oh, video now.
The skill of the archer relies on his accuracy, his coordination, and his sheer brute strength. There are over 600 muscles in his body, and it takes the combined effort of many of these to pull back the bowstring. To discover the source of the archer's power, we must travel under the surface of his skin. For here lies his muscle, a thick, dense material coloured bright red due to a rich blood supply, which is essential for it to function effectively. In his extended arms, the muscles can hold the tension needed to keep the bone in place without changing their shape. The muscles in his shoulders and arms twitch as they maintain this tension. To find out how they contract to produce this force, we must enter deeper inside. Magnified over 6,000 times, we can see the muscle's fibrous nature. The hundreds of fibres within each muscle run parallel to each other along its entire length. Like the weave of a rope, they themselves are made up of a mass of smaller fibres. And it's only when we reach these minute myofibrils that we have finally arrived at the source of the contraction. Within each myofibril, there are bands of two different proteins. The light-coloured protein layers slide along the dark, thick bands. It is the overlapping of these proteins which causes the myofibril to contract. When the two layers draw apart, the muscle tension is released. The strength of the muscle contraction depends upon the number of myofibrils we contract at any one time. With his aim fine-tuned, his muscles relax, and he lets the arrow fly.
Has anybody ever tried pulling one of those bows? It's hard. What's that?
Composite bows are way harder.
Then wooden bows. All I know is the ones that my buddy used to go to Kapilani and shoot, and it's really hard. You just go. Okay, so sarcomeres, this will be your Z disc, the Z disc, or Z line. All of this open area, what do you think that is? All these little bubbles, what is that? Nope. What? Fat? Nope.
Yes.
Gas?
Calcium.
Nope. Nope.
Calcium.
Nope. It's close though, but not calcium.
Yes. Magnesium.
Has to do with calcium.
Tropomyosin.
Troponin.
What stores calcium?
Bones.
In the muscle cell. What stores calcium in the muscle cell? Sarcoplasmic reticulum. This is sarcoplasmic reticulum surrounding a myofibril. So it's associated with all these sarcomeres. All the myofibrils will be surrounded by sarcoplasmic reticulum. When they are depolarized, then the calcium will come out and find its troponin to bind to. The myosin, if you look, there's all these little lumps on the myosin, and in the center there are no lumps. So the lumps are the myosin heads, and the center doesn't have any heads because it's bare. Out here is actin filaments. You can sort of see little fine lines there. You also see that there are a lot of lumpy things in that area, and those are all the supporting proteins, including chitin. It's also in that area. So this is low power micrograph, so light micrograph of skeletal muscle. Shine light through, you see the cross striation. What are these?
Nucleus.
Now it's mitochondria. So a lot of mitochondria in that area. So what is this right in here?
Indonesia.
Nope. Not sarcoplasm. Look at that. What is that? Nucleus. So you're at the surface of a muscle cell. So this is plasma membrane. It's called what? Sarcolemma. And sarcoplasm is inside. Okay, so crossbreed formation, you have to have the myosin attached to the actin binding site. Myosin's head has an ATPase. Changes ATP to ADP and PI. Puts that myosin head in a high energy state. Will sit there in this high energy state, just waiting for an actin binding site. Soon as a binding site is exposed, it's going to move up there and bind to it. Then you get your first power stroke. The myosin will pull, it's got heads all around, so it can interact with 6 actin filaments at a time and pull 6 actins past it. The binding site for actin on myosin, there'll be 2 of them, one on each head. And then the myosin ATPase, also 2 of them, 1 on each head. This flexible region is where the energy is applied when the actin and myosin bind together. Then the ADP and PI, first PI leaves, then ADP leaves. That releases energy in the molecule, and the neck region flexes. That's your power stroke. So myosin has all these little paddles pointing out in all different directions, interacting with actin, forming cross bridges, and that's all the time we have. So next week we'll pick up with the rest of this